Okay, let's do one more lesson on probability. And as I say, we talked about a dice, one die the first time, and we talked about a dartboard last time, and now we're going to talk about two spinners. So you have a spinner where you can spin it, and it either lands on one or two, and then this one you spin, and it lands with equal probability as this one did, but this one with 1, 2, or 3. Okay? So what are all the possibilities for what could happen if you spin both the first dartboard and the second dartboard? So let's make a sample space where the first entry is what happens on the first board and the second entry is what happens on the second board. So you could land on a 1, 1, you could land 1, 2, or you could land 1, 3, or you could land 2, 1, 2, 2, or 2, 3. So you have 6 different possibilities. So let's let event A be that the sum of the two is 4. Okay, what's the probability that A would occur? Okay, well, let's see. For the sum to be 4, this could happen or this could happen. Do you agree? You have 2 out of 6 there. All of these are equally likely. So you have 2 out of 6, which of course is the same as 1/3. And if you want to make a little diagram of what's going on here, A is again, the sum is 4, and so you've got 2 things in there. How about B? B is the same number. So the same number, well, I'll put a little squiggle around it. There they land on the same number, and here they also land on the same number. So the probability of B happening is also 2 out of 6. Agreed? So now let's go ahead and complete this Venn diagram. We've got 2 things in here. We've got 2 things in here, and they have one in common. Your 2, 2 is in both of them. Here is your 1, 3 in here. Here's your 1, 1 in there. These two are both the same, and these two both add to 4. And then what about the other ones? They're all outside here. Here's your 1, 2, and you've got a 2, 1, and you've also got a 2, 3. Okay, so they're all out there. Okay, so that's what's going on. So now let's go ahead and calculate our other things as well. Let's see, the probability of A intersect B. That's going to be just 1 out of 6 things, so that's going to be 1/6. The probability of A or B, and I'll use this to indicate A or B. That means that either this happened or this happened, and so it's the probability of A plus the probability of B, but then here's a probability of A, there's a probability of B, but then you counted this one twice, so you need to subtract the probability of A intersect B, and so you end up with 2, 6 plus 2, 6 is 4, 6 minus 1, 6 is 3, 6, which in this case would be easy enough just to count them 1, 2, 3, right? There's just 3 of them in the union. Okay, in A or B. Let's see. Okay, what's the probability of A given B? Okay. The probability of A given B is, recall, it's the probability of A and B divided by the probability of B. So you know that B happened. Given that B happened, you want to know, did A also happen? So you know you're in here, you know you're in B. Given the fact that you're in here, what are the chances that you're also in A? Well, that would be 1 out of 2, because there's 2 things in here, and one of them is also in A. So it's going to be the intersection is 1/6 divided by 2/6, which is going to be 1/2. Okay, so it's 1 out of 2. What's the probability of B given A? Well, again, that's the probability of A and B happening divided by the probability, here's your universe, of A. And so again, that's going to be 1/6 divided by, what's the probability of A? probability of A is 2/6. So given the fact that you're one of these two things, what's the probability that you're that one? That's going to be 1 out of 2. Okay? So you got that. Are they independent? Are A and B independent? Well, is this the same as the probability of A? No, the probability of A is 1/3, and the probability of A given B is 1/2. So knowing B changed what you know about A. Similarly, knowing that A happened changes what you know about B. Okay? So they are not independent. The answer is no. The other way to check it is just to check to see that the probability of A intersect B is 1/6, and the probability of A times the probability of B is equal to 1/2 times 1/2, which is 1/4. And since those two things are not the same, that means that they are not independent. Okay? So they're not independent. They are dependent, if you want to use that word. Okay? Knowing one tells you something about the other. Are they mutually exclusive? Are A and B mutually exclusive? No, they're not, because to be mutually exclusive means they can't both happen at the same time. And to both happen to not, if they don't happen at the same time, that means the probability has to be 0. Okay. What if we wanted to come up with a couple of events which are independent of each other? Can you think of a couple that would work? Let's get rid of all this, and let's come up with a couple things that are independent. Would you agree that if the first spinner lands on a 1, should tell you nothing at all about what the second spinner does? You agree? Those two things should tell you nothing. No, this should tell you nothing about this spinner. This spinner should tell you nothing about that spinner. So let's let A, B, I need to get myself another marker here. Let's let A be an event that 1 lands on a 1. And let's let B be the event that this thing lands on, say, a 3. Okay? Let's do that. So, okay, so first of all, let's find the probability of A. The probability of A is that this thing lands on a 1. If you're going to have 3 of them, 3 out of 6. So it's going to be 3 out of 6. The probability of B is that this thing lands on a 2. How many of them are going to land on a 2? Here you have a 2 there, and there you have a 2 in the second spot. So it's going to be 1/3, or 2/6. Let's call this one 1/2. And 2/6 is the same as 1/3. Okay? Finally, what's the probability of A intersect B? That's what? This one lands on a 1. So the first one's got to be a 1, and the second one's got to be a 3. Did I say that right before? Let me be clear. For A, the first one had to land on a 1. You have 3 out of 6. For B, the second one had to land on a 3. I might have said 2 before. It had to land on a 3. There's one where it lands on a 3, and there's another one where it lands on a 3. So that's 2 out of 6. 2 out of 6 is the same as 1/3. Okay? What's the probability that they both occur? So the first one lands on a 1, and the second one lands on a 3. That's that one right there. That's 1 out of 6. See that? So in order to be independent, what's got to happen? The probability of A intersect B has got to be equal to the probability of A times the probability of B. And sure enough, this is equal to 1/6. And this is equal to 1/2 times 1/3, which is also 1/6. So sure enough, our intuition that tells us that those two things are independent, that shows itself here. This is equal to this. They're both equal to 1/6. In other words, if I tell you the probability of A given B, given that B happened, what's the probability that A happened? That's the probability of A given B. Let me get another marker. Divided by the probability of B. Okay? So the probability of A given B, I'm sorry, this is the probability of A and B. The probability of A and B is 1/6. The probability of B is 1/3. 1/6 divided by 1/3 is what? Is 1/2. So the probability of A given B is 1/2, and notice that the probability of A is 1/2. See that? So knowing that B happened doesn't change anything we know about A happening. See that? So that's how all those numbers work. So kind of cool, okay? I like all those three examples. Dartboard, dice, and spinning wheels. A spinner, because between all of them, they kind of help you develop an intuition, understanding of probability. So with all that, let's do two more, I think, kind of interesting examples, okay? And again, these just show how things can be kind of strange. You flip two coins, and you don't see the result. You just flip them over a barrier, and you don't see them. Someone else is over there, and they answer the question of whether at least one of them is ahead. And you are told that at least one is ahead. And we're assuming these are fair coins. They're just as likely to be a head as a tail. Okay, so you flip two of them. You don't see either of them. But then you ask the question, is at least one of them ahead? And the question is this. If the answer is yes, then what is the probability that they are both heads? Okay, you flip two coins. You're told that at least one of them is ahead. And what's the probability that they're both heads? Now, here's what I like about this. If I just flipped one coin and then it's a fair coin, what would be the probability it would be a head? The answer would be 1/2, right? 50%. So if I flip one coin, I'd say the probability that it landed ahead is 1/2. Okay, now I flip two coins, and you look at them, and you say, hey, at least one of them is ahead. What's the probability that they're both heads? So some people would kind of think, well, to say that one of them is ahead is to maybe get rid of this one, and now what are the chances that this one's ahead? It's still 50-50. It's still 1/2. But that's different from, well, let's first answer this question. To answer this question, let's look at the sample space. The sample space would be that they both landed head-head. They landed head-tail. Maybe this is the first coin, that's the second. Maybe this is a penny and that's a quarter. There's your penny, there's your quarter. There's your penny, there's your quarter. And here's your penny and here's your quarter. So you got two different coins. And so those are the four different equally likely possibilities that may happen. Okay, do you agree they're equally likely? And now you're told that one of them is ahead. So the fact that one of them is ahead gets rid of this one. So now you know that one of those three things happened. Those three things are all equally likely, but that's your new universe now, see? There's your new universe. So this is conditional probability. You're told that one of them is ahead, so there's your new universe. Now, given that, what are the chances that they're both heads? And now you can see the answer. 1 out of 3. 1 out of 3. Instead of 1 out of 2, it's 1 out of 3. See that? So that's different from if I would have thrown a penny and a quarter and then asked you, is the quarter ahead? If we agreed beforehand that you were going to tell me what the quarter was, and you said, oh, the quarter landed heads. That's different, because what did we say the quarter was? The quarter was this one or this one. So if you tell me that the quarter landed heads, then I know that it's one of those two. Neither of these are there. Okay, the quarter, the last one landed heads. What are the chances that the penny landed heads? That would be 1/2, 1 out of 2. Okay, so that would be your new world. But if you just say, without me asking you, you just say, hey, one of them landed heads, then you've got 3 possibilities there, and the answer is 1/3. So they're very subtle. Remember what I said in the first lesson? These probability things, I guess I was talking about counting, can be very subtle. Okay? Here's another one. Similar idea, but more deadly. Okay? You got 3 men in prison. Okay? You've got Al, Bob, and Carl, A, B, and C. Okay? And these men all know that one is going to be executed, let's say hanged, and the other 2 set free. Okay? They all know that. That's all true. They all know that. And so the jailer comes to the cell, and L says to the jailer, hey, I know that at least one of these other ones is going to be set free. Maybe they both are. Maybe I'm the one that's hanged, but I know that at least one of them are going to be set free. So go ahead and tell me one of them that's going to be set free. And the jailer says, okay, I'll tell you, Bob is going to be set free. And the question is, if the jailer tells if the jailer tells L that Bob is going to be set free, does that change L's chances of getting hung? Before he knew that, his chances of getting hung were 1 in 3. Agreed? If he now knows that Bob is going to be set free, does that mean that now he has chances of 1 in 2? Because he knows that Bob is going to be set free, and so it's now either him or Carl. Does that make a difference? So is his probability the same as before? Because as he said, he knew that one of them was going to be set free. So does that give him new information? Does that really give him no new information so that he still knows that he's 1/3? Or is it the case that now he has chances of 1/2 of being hanged? Okay? So what do you think? What do you think? Here's the answer again. The answer is similar to the previous one. You can go through all the work with this, but basically what it amounts to is, as long as he just asks the jailer, tell me one of them that's going to be set free, and the jailer says, okay, I'll just tell you that Bob's going to be set free, that doesn't change anything. That doesn't change anything. Really what it means is that Carl should be feeling just a little bit worse right now because of the 2 choices. He didn't mention Carl, he mentioned Bob, okay? So now Carl is going to have 2/3 of a chance of being hanged, and Al is going to end up with still 1/3. On the other hand, if Al would have asked the jailer, I want to know whether Bob is going to be set free or not. Okay, so Al is the one that says to the jailer, I want to know about Bob. And the jailer says, okay, I'll tell you, Bob is going to be set free. Okay? Now, Bob is out of the picture. Al was the one that did the asking. Bob is out of the picture. Now they're both 1/2. Okay? Now they both have a probability of 1/2 of getting hanged because he asked him about Bob, and the answer could have been Bob is going to be hanged, but instead he just says, what about Bob? And the answer is Bob is going to be set free, and so now the chances are equal for both of them. Okay, so kind of cool. So again, this is it's called the prisoner's problem, And it's also called the Monty Hall problem because there used to be a show called Let's Make a Deal where you had 3 curtains, and after picking one curtain, then the master of ceremonies would show you some booby prize behind the second curtain, maybe a goat eating a bunch of oats or something, some crazy booby prize. And then the question is, given that you know that this is a booby prize, do you want to switch over to this one now because you know that there's a big prize behind one and there's booby prizes behind the other two? Are you better off to switch to this one, or should you keep the one you had? So a lot of interesting problems. That one has been worked on by lots of mathematicians. It's also talked about in your book. Okay, very good. So that's probability theory.